Good morning, good afternoon, and good evening for those of you joining us today from around the world. My name is Allison Douglas, and I'm a Market Development Manager at Agilent Technologies, and I will be your host for today's webcast entitled LTE and the Evolution to LTE Advanced Fundamentals. This webcast is the second in a series designed to provide a strong foundation for RF engineers learning 3GPP LTE technology. Joining us today is Jan Whitaker. Jan has over 30 years of engineering experience in cellular technologies. She currently works on solutions from across Agilent focused on LTE, LTE Advanced, and wireless LAN. She coordinates communications, is the author of many articles, and creates and presents training courses. She's also the project lead and a technical contributor to Agilent's LTE and the Evolution to 4G Wireless books. We'll begin today's webcast in just a moment, but first a little bit about the process. Jan will answer questions today at the end of her presentation. To participate in the Q&A session, you can enter questions at any time during this presentation in the question window on the lower right-hand side. Be sure to address your questions directly to all panelists by clicking on the pull-down menu. We have a lot of people online with us today, so I apologize in advance if we don't get to all of your questions. But don't worry, if we do run out of time, we will respond to the remaining questions via email. We will also email you a link when the on-demand version of this presentation is ready to view, along with a copy of the slides presented today. We also ask that you take a moment to fill out the short feedback form that will appear when you close the WebEx session. Now let's move on to the presentation. Welcome, Jan. You now have the floor.
Thanks, Allison. Welcome to the second part of this two-part series on LTE and LTE Advanced Fundamentals. This webcast is based on our new second edition book titled LTE and the Evolution to 4G Wireless. It was created by over 40 engineers and provides a reference for engineers working on design and test of LTE technologies. The second edition added over 200 new pages, adding a lot of detail on LTE Advanced and many other areas. Here's our agenda for today. I'm going to start off by talking about MIMO concepts. I won't go into a lot of detail, but I hope to give you the basics for further learning. I'll then talk about LTE Advanced major features and some of their design challenges. I'll do an overview of RF conformance and acceptance testing, and then I'll follow up with questions and answers. All right, so let's start off with talking about multi-antenna techniques. The overall goal is to increase coverage and physical layer capacity. There are three main multiple antenna application categories. The first makes direct use of path diversity, in which one radiated path may be subject to fading loss and another may not. So one signal bounces off the building while another signal goes directly to the mobile. We take advantage of the difference in those two signals. So diversity can be introduced at either the transmitter, the receiver, or both simultaneously. The second application is to apply beam steering. Beam steering, as its name implies, is associated with the physical steering of the RF signal by controlling the phase and the signals radiated from the antennas so they are directed at the receiver. So it's the direct signal, the red line in this diagram. A third application is to separate the antennas in space to enable the use of spatial multiplexing. Spatial multiplexing allows for the simultaneous transmission of more than one stream of data in both time and frequency. Now, you also hear the term beamforming when you read about MIMO. Beamforming is a more complex technique that is used to further enhance the transmission. It is called beamforming when feedback is used to adapt the signal to channel conditions. The transmitted signals can be modified in either amplitude, phase, or additionally cross-coupled. So let's dig into more detail on path diversity and spatial multiplexing. First, let me say that when we you see the term I and O in these figures, this refers to going into the channel and out of the channel. It does not refer to the antennas. So employing a single antenna at the transmitter and a single antenna at the receiver, single input, single output, or SISO, is the most basic radio channel access mode. And that's this one up here, right here, okay? Below here is SIMO, and this is receive diversity. So you have one transmitter and two receivers. SISO is suited to low signal-to-noise conditions, such as operating at the cell edge or fading. There is no improvement in peak data rates, though. But SIMO is more robust in difficult radio conditions since SIMO operates at a lower signal-to-noise ratio. So up here on the right is MISO. MISO is transmit diversity. It's a technique that only requires a single receive antenna. So like SIMO, though, it does not increase the peak data rates. And the last one here is multiple input, multiple output. MIMO can increase spectral efficiency and channel capacity. So two different signals that are shown by two different colors, the orange and the blue, represent two different data streams that are sent at the same time and frequency. Two different signals are received at each antenna. They are then decoded and the user data is retrieved. So in these diagrams, I only show two antennas, but any number of antennas can be used. Let me do a little bit further explanation in some areas here. So SIMO plus MISO does not equal MIMO. So transmit diversity and receive diversity does not equal spatial multiplexing. The difference is that SIMO and MISO only uses a single data stream versus MIMO uses two different data streams. Again, the I and the O refers to the channel. And the diversity can be combined with MIMO spatial multiplexing to improve performance. And one of the key aspects is that for MIMO to work, the paths must be decorrelated. So if the two signals show up at the receiver and they're identical, you get no benefit of MIMO. And you'll see the terms layer and stream. That refers to the signal that's in the channel. The basics of spatial multiplexing operation can be understood by using this static four-part network to represent the channel. So two signals containing different user data are simultaneously transmitted and received. Predefined training signals are transmitted from each antenna at A and B. The receiver knows which training signal was used for each antenna and therefore can calculate the channel amplitude and the phase responses Z1, Z2, Z3, and Z4. The receiver can calculate the transformation that the signals from each antenna have undergone. Since the unknown data is sent at or around the same time as the known training signals, the receiver can assume that the part of the signal containing the unknown user data from each antenna has undergone the same transformation as the known part of the signal. In essence, spatial multiplexing is using a trick of using known training signals mixed with the randomly varying data in such a way that the unknown data can be recovered. So here's a diagram that shows single user MIMO. On the left, we start with user data that we want to transmit from the base station. The user data is put into code words. A code word represents user data before it is formatted for transmission. So it's an important concept again in MIMO. It is then mapped into layers or streams. Then it is pre-coded with information that will match the channel conditions. And I'll talk about pre-coding in just a minute here. The information is sent through the channel where it is faded and mixed, and then it's received by the handset where it is demapped and demultiplexed. And let me explain up here on the top terminology that you see throughout the standards, and I'll use interchangeably. On the left here, we have base station. In the standards, it's called E node B or Evolve node B or ENB. That's the same term for base station. And in the standards, they use the term UE for the handset or the mobile station or the device under test, the handset. So let me define precoding just a little bit more here. So the process of precoding the signals before transmission is to adapt those signals to the channel propagation conditions that the receiver sees. Important concept for MIMO. The signals are modified in amplitude and phase, and additionally cross-coupled between the antennas. So precoding is used to equalize the performance of the two streams of data. So at the top, we begin, the base station sends a signal to the handset. The handset then estimates the channel and picks the optimum precoding from a predefined code book, which both the base station and the mobile have. It then sends a signal back to the base station. The base station then modifies or transforms the signal to match the coded message, and therefore it matches the channel. So let's talk about LTE's very specifically defined downlink transmission modes for MIMO. So the first one is receive diversity. We talked about that. It's basic SIMO. And then the second one is transmit diversity. That's, again, two signals going into the channel and only one receiver to look at the signal coming out. So for the third, fourth, and fifth one, let me go to the next slide. The third one is single user MIMO, and it's also the fourth one. And the difference between the 3 and 4 is open and closed loop. Okay, so open loop means that the base station transmits 2 or more signals into the channel, and then only the one UE receives it, and there's no feedback from the receiver back to the base station. There's no precoding that's being done. So they use open loop transmission when the conditions are changing rapidly, and there's no time for the information to get sent back and forth. The fourth is closed loop, and so precoding is used. This is one of the most common techniques of MIMO that's being used. And this does more to enhance the capacity. The fifth one is called multi-user MIMO, and if you look here, you have the base station, and then you have 2 receivers or two different handsets. And so the 2 receivers that are used are in these 2 different handsets, and this does not increase the data capacity going to each one of those handsets, but it increases the capacity of the network. Now I'm going to go back to the previous slide here, and I want to talk about transmission mode number 6. This is closed loop to beam steering, where the same signal is transmitted into 2 antennas with a phase change that is determined by the feedback from the UE. So closed loop means there's feedback information, and it's used to steer the signal. And then in transmission mode 7, the base station transmits a pre-coded reference signal. So the reference signal is the training signal that's used in the pre-coding. And so in the reference signal, the UE gets its own reference signal versus normally the reference signal is transmitted to all of the UEs in the network. So a code book isn't used because it's real-time channel information is being transmitted specifically through the specific reference signal. Here are the design challenges and some of the requirements for the test equipment. MIMO is complex, and this is why you'll see R&D engineers working late into the night. You also see a lot of universities working on the details or the specifics of MIMO design. For the transmitter with multiple signals, you have to be concerned with cross-coupling within the block diagram. You need to verify that the signals are coded and decoded correctly. Distortion in the power amplifiers is critical because distortion will create signals that fall outside the channel and create interference. It's a major issue for OFDM technology. For the receiver, it needs to recover simultaneous multiple signals and adequately test all the components within the block diagram against real-life conditions, including interference. So analyzers need to be able to pick out the right signals in the spectrum and be able to demod and decode the signal. You also have to be able to look at the spectrum to see if interference is being generated. To test a receiver, you need signal generation to create a wide range of scenarios, including fading and interference. So that is my brief overview of MIMO. Let me move on to talking about LTE Advanced and its major features and design challenges. Here's the timeline for the 3GPP releases of the UMTS technologies, starting in 1999 and going on to today. In the center column is the date when the stage 3 aspects of the technology are frozen for that release. This can be, there can be further explanation of the features, but no more features can be added. Today we're going to talk about Release 10. This is where LTE Advanced is defined, and it was frozen in March of 2011. The most important source of information on LTE Advanced features is within the standards themselves. And here's a link to a summary of all of the LTE Advanced proposals. And we also have included the historic documents, links to those, to help you get the big picture, a further understanding of why things were developed the way they were. So let me compare LTE Advanced and IMT Advanced, the requirements of these. So this is the requirements that were put in place that the technologies and the designers need to design the equipment to. So LTE comes from Release 8 of the 3GPP standards, and LTE Advanced comes from Release 10. And I'll use the term LTE Advanced and Release 10 interchangeably throughout the rest of this presentation. IMT Advanced is a set of requirements from the International Telecommunications Union that was designed to globally be the true 4G standard for the world. And we may talk about that later in questions, but the 3GP committee submitted LTE Advanced to meet the requirements of IMT Advanced to be one of the technologies for the true 4G. So let's look at the comparison of the requirements of these technologies and how they're working to meet the true 4G. So important specification of the peak data rates. This affects the download speed of your video that you want to watch on your laptop or the presentation you want to view. So LTE meets the downlink but not the uplink, and you can see that the LTE Advanced does meet the requirements. Another major issue is peak spectral efficiency. So this is important to the network operators because they have limited spectrum and they need to be as efficient as possible. Again, you can see that LTE didn't meet the uplink, but that LTE Advanced does. And so the downlink did meet the requirements of the IMT Advanced standard. And then also the flexible bandwidth. And so for LTE, we have up to 20 megahertz, and LTE Advanced is up to 100 megahertz. And I'll talk about how we get up to that 100 megahertz bandwidth and far exceeds the IMT Advanced standard. And realize that all of the standards need to be backwards compatible, so LTE Advanced needs to work to LTE. So here are the key features of LTE Advanced that were frozen as part of Release 10. I'm going to talk about all of these here today, but I'll go into more detail on the first three and talk about where the following standards come from. As one of the most distinct features of 4G LTE Advanced, carrier aggregation pulls together multiple carriers to a maximum transmission bandwidth of up to 100 megahertz. So this is how we get that 100 megahertz, is by aggregating up to 5 LTE 20 megahertz carriers. So each carrier, when they're pulled together, or each carrier is called a component carrier, so CC. So this is a CC here. The main requirement of LTE Advanced is to increase capacity or data rates. So the most obvious way to do this is by utilizing more of the spectrum. So that's the first place you go, is to use more spectrum. Again, we were talking about the 1 gigabit per second in the downlink and 500 megabits per second in the uplink. And so in order to do that, this is one of the ways to help achieve that target. So in addition to getting the higher data rate, there's another motivation to help that we're using this technology for. It's to more efficiently use the fragmented spectrum. In practice, for the operators, this is more important since there is a large variety of fragmented spectrum that they have, and carrier aggregation allows these fragmented spectrum to provide the higher data rate services. And the third motivation is intercell interference management, and this is beneficial in a heterogeneous deployment where cells of different power levels and coverage areas are supported. So you can pick and choose where you're going to transmit to avoid the interference areas. There are 3 aggregation scenarios possible depending on the spectrum availability of the operators. As seen on this slide, aggregated component carriers can be contiguous or non-contiguous with both within a single frequency band or 2 different frequency bands. So the top image shows a single band or an intra-band contiguous carrier aggregation with 5 20 megahertz component carriers. This is a less likely scenario given frequency allocations today. According to research done by Ericsson, 90% of all contiguous spectrum is less than 15 megahertz. The middle image shows us non-contiguous allocation in the same frequency band. This may be used when the middle carriers are loaded with other users or network sharing is considered. And finally, the bottom image shows us non-contiguous allocation in different frequency bands, also known as interband non-contiguous carrier aggregation. And this is going to be the most realistic scenario given the spectrum service providers have. One of the drawbacks of this scenario, though, is the complexity of the RF front end of the user equipment. The antenna size, the power amplifier, the filters, etc., may not be compatible with the different frequencies. So the first thing that standards groups have to do and had to do was to define the different combinations of the frequency bands that could be used for release 10. So for release 10, they've only chosen 3 different combinations, and you can see those over here on the left. And these only have 2 component carriers in there, so up to 40 megahertz. For release 11, though, they've added all of these bands, and these are have been proposed by, you can see the network operators, and they're utilizing the spectrum that they have. So each one of these combinations requires a study for the coexistence. And then, of course, each network equipment manufacturer has to design the devices to work within these frequency bands. So let's look at the challenge of intra-band carrier aggregation. It's not such an issue for the base station at this point because they have already been working to deal with multiple carriers in MIMO. But it's a major challenge now for the handset or the UE. So from an RF perspective, intra-band contiguous aggregated carriers have similar properties as corresponding to a wider carrier being transmitted and received. So it's just wider in the frequency range. On the right is a CCDF, or a complementary cumulative distribution function. A point on the CCDF curve indicates the probability as a percentage of individual power measurements that the signal will reach a given peak level above the measured average power level. So in this case, the CCDF plot shows that 2 contiguous component carriers, that's the yellow line here, has a higher probability than a single carrier of having a peak data signal more often. 2 carriers then requires an improvement in the power amplifier linearity, or a reduction in the maximum operating level, putting more stringent requirements on the transceiver chain. For inter-band carrier aggregation, the major challenge for the UE is it has to have multiple transmitter and receiver chains being operated simultaneously. So here are the 2 different chains. So when you have multiple transmit and receive chains operating within one device, it creates a very challenging radio environment in terms of intermodulation and cross-modulation. So let me talk about the second major feature of LTE Advanced. It's a combination of clustered SC-FDMA, so that's the Uplink technology that's used, and it also has added simultaneous transmission of the PUSCH, the share channel, that's where the payload is, and the PUSCH control channel. So in Release 8, over here is Release 8 scenarios, and each one of these are different potential scenarios. Only one signal is transmitted in the uplink bandwidth. So this is the data channels information, and the blue are the control channels. For LTE Advanced, more than one signal can be transmitted in the channel. So on the left is 1, on the right is 2. This allows non-contiguous clustered groups of subcarriers to be allocated for transmission by a single UE. This increases the flexibility available for frequency selective scheduling. So clustered SC-FDMA was chosen in preference to pure OFDM, which is used in the downlink, in order to avoid a large increase in peak to average power ratio. In Release 8, the user data carried on the physical layer uplink share channel. These are the blue signals now. And the control channel, this is the control channel, the red is the share channel. They could not be transmitted at the same time, but for LTE Advanced, they allow for simultaneous transmission of both. This mechanism has some latency and scheduling advantages over time multiplex approaches, but it does generate multiple carriers. So let's look at the signal here. On the left is an actual signal. It shows two shared channels and then one control channel. And on the right side is the CCDF curve. Okay, again, that's the probability of peak power levels. And you can see that it's gone up for this new transmission type, but it's still better than the Gaussian noise or the level that you would have for true OFDM technology. Let's talk about another design challenge here. Here's the typical spectrum of a single carrier with 2 resource blocks at the channel edge. So here's 2 resource blocks at the channel edge. Here's the LO feed through in the image, and here's the spurs that are created with this signal. Now let's move one of those signals, one of those resource blocks, over to the other side. And you can see that there are 2 carriers here now, and you can see that they're interacting with the LO. And look at the spurs that have popped up. So it's 25 to 30 dB or 50 dB worse. So designers have to be concerned with the intermodulation or the interference that comes with the signals that are mixing. Okay, I'm moving on to the third feature of LTE Advanced. It's MIMO. We're adding more to MIMO. It can be up to 8x8 in the downlink with 4x4 as the baseline. And it can be up to 4x4 in the uplink with 2x2 in the baseline. And there's a lot more work happening with the beamforming that will give it the advantage of the higher data rates or coverage or capacity. We've added 2 more transmission modes to that list of 7 that I talked about earlier. And in these transmission modes, they do more, they add more UEs to the multi-user MIMO situation, and they also do a lot more work with UE-specific reference signals. So a lot more work in having real-time feedback to the specific handsets. Adding more MIMOs, this is my little humor. Our phones are going to start looking like hedgehogs with all of the antennas coming out of them. Okay, design challenges for MIMO. Higher order MIMO has a similar impact on carrier aggregation, or a similar impact as carrier aggregation because you're adding more carriers into the system. And so there's the additional challenge that if you have a carrier aggregation of 5 carriers and then you have 4x4 MIMO, you could have up to 20 antennas on your base station or your handset. And realize that all of these have to be decorrelated. The signals cannot come in the same. So that means that you have to have spacing or some distance between the antennas, which can be a real challenge in the handsets. There's also a lot of work happening on testing for MIMO. So conducted testing, or being able to hook up cables to measure the performance of MIMO, just isn't going to work. So you need to have over-the-air testing, and there's a lot more complexity with that because of the complex interaction of the signals. So those were the 3 key features of LTE Advanced that were part of the formal Release 10 that was proposed to meet the IMT Advanced standards. But there's a lot of other work that's going on by the 3GP committees and follow-on releases, and I'm going to talk about some of those key features or key areas right now. So the first one is Heterogeneous Networks. So Heterogeneous Networks is a way to expand the capacity and coverage by adding cells. And there's many different kinds of cells, which adds to the complexity. So in this diagram, we have the macro cell, but then we also have micro and pico cells. We have femto cells. We have remote radio heads or distributed antenna systems, and we have relays. And then you also have multiple technologies. So you have the HSPA, you'll have the CDMA technologies and wireless LAN along with the LTE technologies. So each of these components offers something to the operator. Overall, they give more flexibility and speed to deployment. The network cost of these smaller cells, as well as the installation and maintenance, is less than the macro base stations. In addition, heterogeneous networks use less power, and on both the network and the handset side. And the main issue really is going to be around the management and the backhaul of all of these different types of cells. In the HetNet environment, the new co-channel interference scenarios arise. Various cell types, radio technologies, and backhaul types and cells are deployed within cells. So new intercell interference coordination solutions will be required. Heterogeneous networks interference is more complicated to manage than homogeneous interference issues, which generally have happened at the cell edge between 2 base stations. The second bullet talks to self-organizing network, and I'll talk about that as another feature in a few slides. And then the last bullet talks to the necessity for operators to support strong interworking between LTE and these new types of cells and the legacy networks. They need to ensure that their customers with the latest devices have a good user experience when they roam around the network. So testing handovers is going to be critical. And there's also the added complexity of the different backhauls between the WLAN and femto cells using the internet and the base and the macro cells and the pico cells. Okay, so another feature that's been talked about for quite some time is coordinated multipoint. It's an advanced variant of MIMO, and it's being studied to improve the performance, again, for higher data rates and system throughput. Another name for it also is network MIMO. It extends the MIMO concept by coordinating different base stations to provide beamforming and spatial multiplexing capabilities between 2 adjacent cells. And the focus is on the cell edge users. So this study item has been under consideration for some time and is still currently in study in Release 11. So what's the difference between these 2 graphics? At first I didn't see it, but this transmitter over here is physically located in the same place, and this graphic here, these are 2 transmitters and they're physically separated. And the difference here is we need to make sure that we have a link between the 2 base stations. It has to be a high-speed data link because it's sharing the baseband or the payload information. Within the confines of a single device, whether a UE or a base station, the sharing can be accomplished on a chip or between modules. But in cooperative MIMO, there's distances maybe up to even kilometers, several kilometers. So sufficient backhaul transmission bandwidth with the necessary latency, can't have a delay, is a considerable technical challenge. Another method for improving coverage is in difficult conditions is the use of relaying. So the main use for relays is to improve urban or indoor throughput, or to add dead zone coverage, or to extend coverage in rural areas. The most basic method is a radio repeater, which receives, amplifies, and then retransmits the downlink and uplink signals. So in this figure, the repeater could be located on the cell edge or in some other area of poor coverage. Radio repeaters are relatively simple devices operating purely at the RF level, so they don't have the signaling, so they just transmit the signaling directly. So the main operational challenge with getting relay to work will be the management of the UE. So the UE has to hand over to the relay node when in range, and then it has to release it when it's out of range. So if this process isn't managed well, the performance is going to go down. Home E Node B mobility enhancements. So home E Node B are really femtocells. So the femtocells are not new to LTE Advanced, but there's a lot more work going on in place here. In Release 8, they were introduced as part of UMTS. From a radio perspective, the femtocell operates over a small area within a larger cell. So the femtocells are within these homes here. It's fundamentally different from relaying since the femtocell is connected into the core network through an existing DSL or an internet cable. So the relay gets all its information from the macro cell over the air. In this case, it gets its information from the internet. So most femtocell deployments will be indoors, which does help to provide isolation between the femtocell and the macro cell. And in Release 10, they've done further enhancements to have them be able to talk to each other. Another feature here is customer premises equipment. This, or CPE, this refers to a UE in a fixed location, which can be either indoor or outdoor. The advantage of CPE is that it can be optimally located using a higher performance antenna. It operates at a higher output power, it's specified at a higher output power than a standard UE. And it can be plugged into a power source, so you don't have to worry about battery drain. Okay, the difference between this and a femtocell, no connection to the internet. So all of the information is being transmitted back and forth from the macro cell. And the last feature I'm going to talk about is self-optimizing networks. Today's cellular systems are very much centrally planned, and the addition of new nodes to the network involves expensive and time-consuming worksite visits. A self-optimizing network can substantially reduce the efforts required to introduce new nodes and manage the networks through self-configuration. So there are a number of use cases in which SUN could be applied. So self-establishment of a new node, self-configuration, self-healing, continuous optimization, capacity and coverage optimization. So in Release 8, they introduced a basic version of SUN, including automatic neighbor relations, list management, and self-establishment of new base stations. And in Release 10, they're working on the management aspects for interference control, capacity and coverage optimization, further work on that, and then random access channel optimization. So important for the network operators. LTE Advanced Deployment. So if someone asks you about when this will be deployed or how it will be deployed, the first question to ask is which feature, because LTE Advanced, as you can see, is a collection of a lot of different features. We think that the first ones to be deployed, well, it's pretty obvious. The first to be deployed is carrier aggregation. We already see chipsets that are using this technology. It'll be 2 component carriers. And of course, there'll be work done with a MIMO in both the uplink and the downlink. So that's it for LTE Advanced, and now let me do an overview of RF conformance and acceptance testing. Here are the phases of testing within the device or the base station life cycle, and this is where the conformance fits in here. The goal of LTE conformance test is to ensure a minimum level of performance. The 3GP standards group defines the conformance test. Conformance testing is done by an authorized test laboratory, and the developer of the handset or base station needs to schedule time for testing their units by an independent third party. And I'll talk a little bit more about certification in a few slides here. But first, let me talk about the conformance tests that are part of the 3GP standards. First off, let me say also that there are more degrees of freedom than any previous radio standard with LTE. And this has a direct impact on the number of tests that can be carried out. So, you know, we have 28 frequency bands. We have 6 different channel bandwidths. There's multiple modulation formats, multiple MIMO configurations, a lot of interoperability that has to be tested out. So all of these need to be considered in the conformance standards. So the LTE conformance standards are divided between the handsets and the base stations. And the handsets is divided up into 3 categories for RF, for radio resource management. And again, radio resource management is, it controls, assigns, and distributes the radio resources among the antennas, among the entities. And then it has signaling. And then for the base station, they just have conformance standards for the RF. So for each of the RF conformance standards, they divide it up into transmitter, receiver, and performance requirements. So just as a reminder, performance measurements determines or measures whether the device is performing as it should. So for example, is the shared channel sending the data correctly and having the closed loop information being sent back correctly to the base station. Here's all the transmitter and receiver test cases. Not going to go into any detail here. One point worth noting in the difference between WCDMA and LTE is that there is an addition of tests for spectrum emission mask, SEM, and adjacent channel leakage ratio. These additional tests come from the need to control the out-of-band emissions, which is more of a concern for the OFDM technology. And also the other area that's different for receiver tests, in LTE they just use block error rate, versus WCDMA did both bit error rate and block error rate. Here's the structure of the conformance test. They define the test purpose, test applicability, the minimum conformance requirements, the description, and the test requirements themselves. Because there are so many degrees of freedom within the LTE, you have to carefully define the conditions under which you do the testing so you can compare the results. So for each of the test cases, they set up the test requirements and test channels. So for the UE, it's called a reference measurement channel, or RMC, and it precisely describes the configurations of the signals to make the test, such as the modulation, the channel bandwidth, the number of resource blocks, etc. For the base station receiver, it's a fixed reference channel, and for the base station transmitter, they define their test models as UTRA test models, or ETM, and this was inherited from UMTS. And there are 3 distinct classes of test models defined. So ETM1, ETM2, and ETM3. And I showed some screenshots of test equipment just to remind us that a lot of test equipment vendors include the test model descriptions and pre-setups. So in our software, Signal Studio software, you can select which of the test models or the RMCs that you want to be working with. The configuration of an RF conformance test system. Here's a typical one. Depends on the complexity of the test. Some tests can be performed with just a base station emulator, or sometimes it's called a one-box tester or system simulator. And other tests require additional equipment, including an additional base station emulator if you're going to do handover testing, or you need interference sources for blocking tests, or you need a spectrum analyzer for looking at the spurious emissions. You also need an RF interface module, which provides essential connectivity between the test equipment and the UE under test. And here on the right is an example of a RF test system, the Agilent T4010S. It's a solution for LTE RF conformance testing. This conformance test system provides a comprehensive set of tools that help the user through the process of testing to the conformance standards. And it can be used for pre-conformance before you end up taking your device to the lab to be tested, of course. The 3GPP core specifications are necessary to design the UE, and the 3GPP conformance tests define how to measure compliance against those core specifications. The last step in the sequence is to deliver certified devices to the market. So the diagram shows the two routes that a UE takes to reach the market. The regulatory certification under the administration of national and regional authorities such as the FCC in the U.S. and the CE mark in the European Commission are mandatory to get to market. So this route is mandatory. Industry certification involves the validation of the test systems used to carry out conformance testing, and then the execution of the conformance test suites under controlled conditions. For UMTS and LTE, these two final steps are carried out under the management of certification bodies. So here are the two main certification bodies involved in LTE. The first certification body over here is the Global Certification Forum, or GCF, and this was formed under the umbrella of the GSM Association, the industry body representing GSM and UMTS operators worldwide. It was formed to promote an industry-backed certification scheme and is maintained by GCF members collectively. It's a private organization. Their work is non-binding, but GSMA members are encouraged to promote only UEs that have achieved this GCF certification. The second certification is the body in the United States, and it was formed with PCS. It's called PCS Type Certification Review Board, or PTCRB, and this board provides certification in North America. So both groups set the certification rules, select the test cases and their priorities, they validate the test platforms, and they accredit the test labs. This slide shows the relationship between the different standards development groups, the body, the certification body, the mobile phone manufacturers, the test system vendors, and the certified test laboratories. 3GPP creates the conformance test specifications. The certification bodies do not automatically adopt the entire set. Each certification body selects a group of test cases. And once a GCF work item is clearly defined, test system vendors develop the test cases required by this work item on their test platforms. Each test system vendor selects a certified test laboratory to validate their test cases on the test platform using reference UEs that support the required features for that designated work item. The test laboratory submits a validation report to the relevant certification body for approval, which then enables the test system to be used to certify any UE. So when sufficient tests in a work item have been validated, and it's usually about 80%, the certification body declares the work item active and UE certification begins. So conformance testing does not assure performance that is acceptable to the end user. Okay, important concept. And so after conformance testing, the devices have to pass the acceptance by the operators. The network operators have shifted their position from simply supplying the pipeline through which wireless devices communicate with each other to becoming the gatekeepers, and they demand certain performance and quality out of the handsets that are put on their network. So what they do is they institute test methodologies for verifying whether the devices have adequate performance and adequate security functions too. And while the conformance is the formal step currently required of all devices, before they are allowed to connect to the network, the operators frequently do more rigorous acceptance testing before they send it out. This figure here shows the influence that the network operators are having on, do have on the equipment manufacturers. So the network operator cares about how their customers will perceive the products they will be selling, and one method is to create these different usage profiles of the customers, and then they develop the test scenarios based on these usage profiles. A lot of automated testing, obviously. Okay, so then network operator acceptance tests tend to be different specifications tested and measurement limits as compared to the conformance test. So we call this type of testing functional testing. And with many additional capabilities in our handsets, such as Bluetooth, GPS, video capture, streaming, WLAN, all of these capabilities need to be tested and how they interact with each other. And one of the key areas is in battery performance. So that's the end. That's my close on conformance and acceptance testing, and I just want to mention that we covered release 8, 9, and 10 today, and the standards group keep working and moving forward with new features and capabilities. So they have frozen the key radio features for release 11 in September of last year, and they're currently working on release 12 with a freeze on the stage 1 part of the release 12. And so more work on coordinated multipoint and a lot more work on MIMO and heterogeneous networks. And I've got to put in my plug here for Agilent. We offer the widest range of solutions for helping the LTE ecosystem get its products to market faster. The portfolio starts with early design on the left and continues all the way through to manufacturing and deployment. We offer more than components. We offer our engineers integrated solutions with the greatest flexibility in hardware, instrument firmware, and application software. And I'd also like to point out down here in the bottom, we have a new capability in our N7109 multi-channel signal analyzer, and we can make measurements on those 8x8 MIMO signals. And of course, I need to make sure that you're aware that we have all these resources available for you to continue learning on LTE. Key area to go is to go to the Agilent site and go to Find LTE, and you'll find all our application notes, a link to our book, our webcasts, our videos, demos, and we also have a lot of webcasts on more details of any of these different areas that we talked about. And now I'll turn it back over to Allison for questions.
Great, thank you, Jan. So we have a few questions today. The first one is, what are the bandwidths for LTE and why are there so many?
Okay, so the bandwidths for LTE are 1.4 megahertz, 3 megahertz, 5 megahertz, 10, 15, and 20. And the reason they have chosen these different bandwidths, it's much easier to do this with the OFDM technology, and it gives a lot more flexibility and helps the operators save resource spectrum, because in some cases for a voice call you don't need as much spectrum as you'll need for that download of the video. So it gives a lot more flexibility in the, for the operators and for the technology.
Okay, thank you. Next question. Why did they pick SC-FDMA for the uplink?
Okay, so It's a good question, and in the previous webcast we talked about the technology. The primary reason was to have lower peak to average power ratio for the uplink, and that's so when they're doing the design of the handset, the amplifier is where you're very concerned about the peak to average power ratio, and it puts less stringent requirements on that power amplifier in that handset.
Okay, thank you. Next question, is there test equipment that can look at the component carriers at the same time?
Yes, thank you for asking the question. So with both the MIMO and the carrier aggregation, now you have you need to be verifying operation and looking at multiple carriers and multiple frequency bands. And Agilent has the spectrum analysis capability in the hardware with our PXA and our MXA spectrum analyzers, and then we have this very powerful VSA software, the 89600, that a lot of work has gone into creating the software so that you can look at these signals simultaneously and analyze what's going on.
Okay, great, thank you. Next question, how do you add impairments for MIMO testing? Well, there's different ways to do that. You need signal generation, you need baseband signal generation if you want to add capability for looking at fading. The Agilent has a baseband generator and channel emulator that can be added to the test equipment diagram or the test equipment setup and add in the different types of fading or the different impairments into the signal. Okay, thank you. Next question, what is DAS on the heterogeneous network slide, and does it increase data rates? Okay, so DAS stands for Distributed Antenna System, and it's essentially moving the antennas away from the cell in order to get more distance in spacing between the antennas, but it does not improve the coverage. It, it does not include the data rates, but it improves the coverage of the signals and within that cell. Okay, thank you. And next question, I see the network operators using the term 4G. What technologies are they using for that? Well, 4G is fascinating. It's been interesting to watch what's happened in the industry in the last 2 or 3 years as we watch the network operators advertise in the media the technologies in order to convince customers to buy their devices and to use their network. So, as I said earlier, the true 4G technology isn't really out there until LTE Advanced is operating at the 1 gigabit per second data rate. So, what happened was as people started to deploy the higher capability of HSPA Plus and WiMAX and the LTE technologies, they started calling it 4G, and the ITU group came out and said it was okay for them to use the term 4G. So 4G that you hear advertised, it could be LTE, it could be HSPA Plus, it could be the 1X VDO technology, could be WiMAX. And what's really interesting for me is what will they call IMT or the LTE Advanced technology? What will AT&T or Verizon or Vodafone call the follow-on technologies? Well, interesting you should say that, because there was also a question if there's any talk about 5G. Well, yes, of course. You know that there's, with the internet and all of the people out there being able to talk about technologies and blog about it, yes, of course, there's a lot of discussion on 5G. Not a lot, but there's already discussion on it. But the reality is yes, there is research going on. There are universities. The European Union has put forth money
for universities and for companies to work on what 5G would look like. They're talking about it being 10 years out. And the requirements, it looks like from the different groups is 10 gigabits per second and a round-trip latency of 1 millisecond, and of course supporting the Internet of Things. So not just having mobile handsets, but having everything connected to the Internet. So yes, there will be a 5G, I'm sure. I'm not sure if that's what it will be called, but they are continuing to look forward.
Okay, great. Thank you, Jan. And it looks like we are at the top of the hour, so that's all the time we have for questions today. I'd like to quickly remind everyone about our survey. Agilent holds many free webcasts throughout the year, and we ask that you take a couple of minutes to complete the feedback form that will appear when you close the WebEx session. This enables us to continue to deliver the content you need. Thanks again for your presentation, Jan. And as we wrap up today, remember that we will email you a link when the on-demand version is ready to view, along with a copy of the slides. Thank you again for attending today's event, LTE and the Evolution to LTE Advanced Fundamentals, brought to you by Agilent Technologies. Please visit us at agilent.com/find/events for more details on our future webcasts. The copyright of the presentation materials is owned